quantum switch, non-Markovian collision model, quantum state reconstruction, weak measurements, quantum thermodynamics, and few more. And so it is my honor to welcome Professor Ghosh for delivering his talk. So yeah, I think, yeah, he has already shared the slide. So it is over to you, Professor Ghosh. Yeah, you can start your talk. But I'm not able to hear you because your microphone is off. Yeah, your slide is visible, but you are not audible. Yeah.
Is that fine now?
Yeah, it's fine now. Yeah.
Okay. So I'll just now I'll unshare it first because I would like to share something else.
Okay.
Yes. Is it visible now?
Yeah. Slide is visible.
Okay.
You have to make it a slideshow.
Okay. Yeah.
Yeah.
Is that fine now?
Yeah. And you are also perfectly audible, so you can start.
Okay. So let me thank the organizer for giving me this opportunity to present this this talk. So is this thing visible? This cursor, is it visible? The moving of the cursor?
Yeah, it is visible. Yeah.
Okay, good. So this is something which I have been doing for last couple of years to understand the notion of incompatibility breaking channel, non-locality breaking channel, and entanglement breaking channel. Actually, to understand the interrelation among these, these states of bipartite or multipartite systems having this property of non-locality or steerability or entanglement. Okay, so let me try to motivate. So this is a part of this work is what I have done with my former PhD student Rajesh Pal some time back, and the rest half is based on some ongoing work with Swati Pandey, Javed Naiku, and Alok Pan. Okay, so let me try to motivate. So this as I said, entanglement, steerability, and non-locality in states of a given bipartite or states of a given bipartite or multipartite quantum system, they form a hierarchy in the sense that all non-local states are steerable while all steerable states are entangled. So such a hierarchy actually is not just of theoretical nature, it is also reflected in practical applications. So for example, entanglement is essential for showing some quantum advantages like teleportation. Steerability is essential for one-sided device-independent schemes, while non-locality is essential for device-independent schemes. Okay. So the question is, this is in terms of the states, these non-locality, steerability, and entanglement. How are they reflected in terms of the dual pictures, namely the quantum channels? Quantum channels means completely positive trace preserving maps. Okay. So maybe we can. So the following question one can. So in this respect, what one can look at is that there will be a actually similar hierarchy. So so if I look at the non-locality breaking channel, this, and the steerability breaking channel and entanglement breaking channels, quantum channels. So if I take the set SEB from H to H prime is the set of all entanglement breaking channels from the set of all bounded linear operators BH to BH prime. This set SEB H to H prime is contained inside the set SB H to H prime. So where SB is the set of all channels from from BH to BH prime, which breaks the steerability of, a bipartite system. On the other hand, this set S, SP, H to H prime is again contained within the set S, L and V of all non-locality breaking channels. Okay, so you have this hierarchy that SEB is contained in SSB, which is contained in SNL. So now the question is, this is fine, but can one get some proper structure of these three sets? That means these set of all non-locality, I mean entanglement breaking channels, ACB, for a given bipartite system, of course, the set of all steerability breaking channels and the set of all non-locality breaking channels. So can one get some structure of these sets? So the other question is, we all know that we can characterize an entanglement breaking channel by looking at its action on one side of a maximally entangled state and see if the output bipartite state is separable or not. Then we can say that if it is separable, then we say that then the channel is entanglement breaking. So entanglement breaking means if it acts on one side of a bipartite state, the output state will be separable. So question is, will such a similar characterization hold good for steerability breaking or non-locality breaking? Moreover, do we have to go beyond bipartite system, namely multipartite system, for characterizing such steerability breaking and non-locality breaking channels? So these are some of the questions that we are interested to look into. Now you can say that what is the point of looking at these non-locality breaking channels, steerability breaking channel, entanglement breaking channel? Because to get quantum advantage, we should get rid of entanglement breaking channel because its action will give rise to separable state. That we will not get any quantum advantage. Similarly, to get semi-device independent schemes, that means where these steerable states are useful, you should get rid of the steerability breaking channels, and same is the case for applications of non-localities. So you should get rid of non-locality breaking channels. Now, unfortunately, the problem with this non-locality breaking and to some extent also this steerability breaking is that the absence of computable necessary and sufficient condition for testing the existence of local hidden variable model. Okay, so whether the local measurements on a bipartite system, the measurement statistics, uh, is it can it be simulated using some local hidden variable model or not? That corresponds to the existence of local hidden variable model. So we don't have a computable necessary sufficient condition in general to test existence for local hidden variable model, except for the case of the Bell-CH inequality, where we have two parties, two measurements per site, and each measurement is two outcome measure. So what we will discuss here is, to a limited extent, the interplay between incompatibility breaking qubit channels. Incompatibility means which breaks the uh, you know if it acts on a set of observables, the observables will become compatible. That means they are jointly measurable. So these interplay between incompatibility breaking channels and non-locality breaking channels in the case of qubit channels from the perspective of Bell CHSH scenario, because as I said, we don't have much choice, other choice. We can't, there is no necessary sufficient condition for other inequalities. And we'll also talk about these a little bit about this wetlethness inequality, which provides a testing ground to test genuine non-locality of tripartite or higher number of parties of states systems. So in this case, we will talk about three cases. Okay, so this is the outline. So I'll first discuss about the necessary sufficient condition for satisfying the Bell CHSH inequality for any two qubit state. This is well known, but still I'll go through it. And then I'll talk about these non-locality breaking qubit channels from the perspective of this Bell CHSH inequality. Then I'll talk about these unital qubit channels in the Bell CHSH non-locality breaking scenario, and we will show that these such a unital qubit channel is non-locality breaking from the Bell CHSH perspective if and only if it breaks um, the non-locality through Bell CHSH again of two qubit maximally entangled states. So it is somewhat similar to the entanglement breaking channel scenario. Okay, so I'll use another file where I'll show that if the conjugate qubit channel, so uh, you know, for each channel I can define its conjugate. So if the conjugate qubit channel is two this incompatibility breaking 2 IBC, then the channel E is Bell CHSH non-locality breaking. This is what I'm going to show you and going to argue. On the other hand, if a channel, this is again a qubit channel, E is unital, and if it breaks the Bell CHSH non-locality, then its conjugate E dagger is 2 IBC. Okay? So these two are, not converse of each other. Basically, you will have to restrict to unital qubit channels. And we'll discuss about this interplay of non-locality breaking and incompatibility breaking qubit channels um, through these Svetlichny's inequalities, of course through example, because even for Svetlichny's inequality we don't have a necessary sufficient condition when a 3 qubit state will satisfy this inequality. Okay, and then I'll conclude. Okay, so let me talk about this necessary sufficient condition for satisfying the Bell CHSH inequality for any 2 qubit state. Okay. So, uh, so this is all well known from the literature, but still let me go through it. So we know that any 2 qubit state row will have a this Hilbert-Smith representation where I can write it. This is a normalized state. 1/4 is I2 cross I2. So I2 is a 2 by 2 identity matrix. R dot sigma tensor product I2, I2 cross S dot sigma, plus this TMN, sigma m cross sigma n, where this TMN is the correlation matrix. This is a 3 by 3 real matrix T rho, and S and T are real vectors. So this representation, of course, satisfies the condition that rho is a Hermitian matrix, its trace is 1, but its positivity will depend upon the choice of this S vector, T vector, and this correlation matrix. So, then that is more involved condition, positivity of rho. Okay. But we know that, so anyway, so that I'm not going to consider here. We assume that this is a density matrix. Okay, so when we talk about this Bell CHSH inequality, basically we have two systems. Alice and Bob has two level systems, each of them. Alice has one two-level system, Bob has another two-level system, and then Alice has choice of one of the two measurements, a dot sigma, where a is a unit vector in R3, and a prime dot sigma, and Bob has one of the two measurement choice, b dot sigma and b prime dot sigma. Again, b and b prime are the unit vectors in R3, and you consider basically this Bell operator. So a dot sigma tensor product b plus b prime dot sigma plus a prime dot sigma plus b minus b prime dot sigma. So this is the Bell operator that you will consider. And we say that a 2 qubit state row satisfies the Bell CHSH inequality corresponding to the choice of this observable A prime, B prime, provided its average value. Bell observable, of course, is a Hermitian operator. The average value of that Hermitian operator with respect to the 2 qubit state is less than equal to 2. I mean, you can take, actually, one should take modulus of this trace less than equal to 2. That is the Bell inequality. But that's it. Okay. So rho will satisfy the Bell CHSH inequality with this one if and only if one can get condition on the parameters of rho, and that is given by if and only if the sum m rho of the largest and the second largest eigenvalues of this T row transpose T row. This is a positive semi-definite matrix. If the sum of the first, the largest eigenvalue and the second largest eigenvalue of this E row is less than equal to 1, then we know that rho satisfies this Bell's HSH inequality. Otherwise, it will not. So this is the necessary sufficient condition for uh, for a 2-qubit state to satisfy the Bell's HSH inequality. Unfortunately, such a necessary sufficient condition is absent for any other Bell type inequality in the derivative. Okay. So now let me talk about these Bell's HSH non-locality breaking qubit channels. Um, so this a completely positive trace preserving map, which is called a quantum channel, which I denote by n, which acts on the set of all bounded linear operators on the Hilbert space HA to bounded linear operators of Hilbert space HA prime. This is said to be non-locality breaking. So this is a general picture, not necessarily restricted to qubit channels. So this is a non-locality breaking channel if and only for every bipartite state rho AB, irrespective of the dimension of HB and irrespective of whether B is a single or composite system. I don't care about that. Okay. The measurement statistics of the output state. So I apply the channel on A side, I get this rho prime, the state, bipartite state. If it has a LHB model means that the probability of getting outcome A for some measurement choice X on a prime system and probability of getting outcome B for measurement choice Y on B system. So this is the quantum mechanical expression for this probability. If it has this local form, so lambda is the shared random variable, and these are the local probabilities PA prime and PB. Okay, so this is the local hidden variable model. So I'll say that such a channel is non-locality breaking if for every such state rho AB, such a condition holds true. It has the output state has local hidden variable theoretic model. Now, as you know, given these definition, characterizing these non-locality breaking channels is quite difficult, as there is no computable scheme for identifying states having local hidden variable theoretic models. So we don't know that, except for very few examples. Okay. Um, so what we will do is we will rather go by through Bell inequality, Bell type inequality, because that is more tractable in our you know so what we can do is we can look for the satisfaction or violation of some Bell type inequalities. So Bell type inequalities are basically some linear combination of these joint probabilities, where this linear combination is less than equal to S. So that will be the Bell type inequality. So remember that Bell CHSH is a specific form of this. Okay. Now, so as I said, even for a generic Bell type inequality, we don't know whether a given bipartite state will satisfy or violate that inequality. This is too difficult in terms of which can be, which is expressible in terms of the state parameters. So that is quite difficult, except for the Bell CHSH inequality. We don't know for other cases. So when you consider the say for example, this will be of course true for any channel, but if I consider for example a qubit channel, n is a qubit channel, then to check for satisfaction or violation of such Bell type inequality, it is enough to consider only pure states. For mixed state it will be easy because mixed state is a convex combination of projections on pure state. Okay. Right, so it will be enough to consider only the pure states. Okay. So here, as I said, because we have this necessary sufficient condition for satisfying the Bell CHSH inequality by any 2-qubit state, so we will concentrate here on the Bell CHSH inequality to characterize non-locality breaking qubit channels. Okay. So for that, what we need is a canonical form of qubit channel. Qubit channel means here the input is a qubit and the output is also a qubit. And one can look at a canonical form of such a channel, which is this 4 by 4 matrix. So this channel has to be trace preserving, and then it is hermeticity preserving and positivity preserving. Of course, we'll put restrictions on this parameter T1, T2, T3, lambda 1, lambda 2, lambda 3, and of course it is completely positive. That means acting on one side of a bipartite state, it should produce a valid state. Okay. So n is unital. If acting on identity, it will produce identity. And basically, what one can look at is you take the Hilbert-Smith form of an arbitrary 2-qubit pure state. I mean, like the one which I mentioned here, this is the Hilbert-Smith form. And then you apply the channel on one side of that state. So like I apply on B side, and then take the sum of the largest eigenvalue and the second largest eigenvalue of T rho transpose T rho, where T rho is the correlation matrix of this I2 cross n acting on 2-qubit state rho. Okay. And if it turns out this m of this quantity, m of this state turns out to be less than equal to 1, then we infer that n is a Bell CHSH non-locality breaking channel. Okay. And if it happens for any such state rho, not just for a single 1 or 2 states, it has to happen for any such state, then only we can say that this is a Bell CHSH non-locality breaking channel. Okay. So now, as I said, in the case of entanglement breaking, we know that a channel is entanglement breaking if it breaks entanglement in the maximally entangled state. So, of course, such a thing does not hold good in general for non-locality breaking channel, even in the CHSH, Bell CHSH scenario. And we will give some example, but there are specific cases where such a result will hold good. Okay. So let me consider the following scenario. So this is what I said, that a completely positive trace preserving map means a quantum channel in BA to B of HA prime. This is entanglement breaking if and only if action of n on one side, let me the A side of projection on this maximally entangled state is separable. Okay. So question is, can you claim the similar thing for Bell CHSH non-locality breaking qubit channels? I mean, can you claim the same thing for other channels also? But for our purpose, it is the Bell CHSH. I mean, it is the qubit channel. Okay. So if I take, for example, this pure state, 2-qubit pure state alpha, which is square root of 0.500 plus square root of 0.5545 and 55. This is a non-maximally entangled state, and apply this qubit channel on, say, the B side, for example. And I have the canonical channel parameters, lambda 1, lambda 2. So like this one which I mentioned, this is the first column, and then this is the lambda 1, lambda 2, lambda 3. All are real numbers, of course. So if I choose this lambda 1, lambda 2, lambda 3, and T1, T2, T3, these are the channel parameters like in this form, then one can figure out that m of this action of, so that is this output state of n acting on one side of this pure state alpha, it will give rise to 1.0159, which is greater than 1. Therefore, this violates the Bell CHSH inequality. On the other hand, if I calculate m of I2 cross n acting on phi plus, this maximally entangled state, it gives rise to 0.994, which is less than 1. So therefore, the output state violates the Bell CHSH inequality. So therefore, you see that for such a channel, okay, satisfaction of the Bell CHSH inequality by the output state for maximally entangled state does not necessarily mean satisfaction by all other states. On the other hand, if I take this depolarizing channel, where P lies between uh, uh, this one, this should be, sorry, this should be half, for P greater than equal to half, less than equal to 1, if I take that, then you will see that this, if I take this channel here, so the lambda 1, lambda 2, lambda 3 are of this form, and T1, T2, T3 are this form. This is, so both these examples, these are non-unital channels. So if I take this channel, then I can figure out that the action of the channel on a maximally entangled state, one side of maximally entangled state, will give rise to non-violation of the Bell-CHSH inequality because this is less than equal to 1. And same is the case for arbitrary 2PV state. Okay? So that also one can show that for arbitrary 2PV state, as I said, it is enough to consider even a pure state. So for arbitrary 2PV state, this also goes. So you see that in this example, if the channel, this depolarizing channel for P greater than equal to half, less than equal to 1, if it breaks the non-locality of maximally entangled state, it will break non-locality of every other state. Okay. Right. So, okay. So now the thing is that, some states like a 2-qubit state, for example, or even any bipartite, any other bipartite state, they may not violate a particular Bell type inequality, uh, whatever be the choice of your observable. But if I apply some local filtering operation, which in more general terms called stochastic LOCC operation, then it may violate the inequality. And such states are said to have hidden non-locality. So to begin with, your state does not violate the Bell inequality, but after this application of these local filtering operations, you basically filter out something which is useful for Bell violation. It will give rise to Bell non-locality. It will give rise to violation. Now, of course, this is not true for arbitrary state. Particularly in the case of Bell CHSH inequality, we have done classification of all such 2PB states which will have this hidden non-locality. And a completely positive trace preserving map N is said to be strongly non-locality breaking channel corresponding to some Bell inequality, of course, because as I said, you cannot have a characterization in terms of the local hidden variable theoretic model because that is too difficult. So if no no stochastic LOCC operation on these output state, so N IB active on rho AB, can make it to violate the inequality, whatever be rho. So such a channel is called strongly non-locality breaking channel. So yeah, so it is, you understand that this is stronger than just simple non-locality. So in this context, if for a qubit channel N, no such stochastic local operation make this output state when N acts on one side of maximally entangled state, uh, no SLOCC can make this to violate the Bell-CHSH inequality, then it can be shown that N is strongly non-locality breaking with respect to the Bell-CHSH inequality. So you see that in the case of this qubit channel, to test a strong non-locality breaking of that such a channel, it is enough to look at the action of the channel on one side of maximally entangled state, okay, in the context of Bell-CHSH inequality. And as a consequence of this result, one can also show that any unital qubit channel, that is identity goes to identity, if such a channel breaks the non-locality, the Bell-CHSH non-locality of a 2-qubit maximally entangled state, then such a qubit channel is strongly non-locality breaking, again with respect to this Bell-CHSH inequality. And as a result of that, we see that any unital qubit channel which breaks non-locality of maximally and 2-qubit maximally entangled state, it will break non-locality of any other 2-qubit state. So you don't have to test for all other 2-qubit states, just like in the case of entanglement breaking channel. Okay, so I have not given proofs of all these results. You can get, if you are interested, you can look at these following papers, like this paper by one of my earlier PhD student, Rajarshi Pal, where you can get to see these proofs related to this Bell CHSH non-locality breaking qubit channels, and then to have a canonical form of 2 qubit states having this hidden non-locality. You can look at this type paper. Um, for an alternative treatment to get those canonical forms. So these canonical forms, which will have hidden non-locality, was based on work of some works of Ghosh and his collaborators. So we have also given a different approach to get those canonical form, which is based upon the polarization optics. And for that, you can see this paper easy way. And there is a recent paper by Franco Nori and his collaborators, which appeared in Spear-X Quantum, where they have given a comprehensive treatment of this non-locality breaking channel, entanglement breaking channel, and incompatibility breaking channel. So let me tell you here is that um, the uh, the steerability breaking. So uh, that means the it is known that um, there is a one-to-one correspondence between steerability of a state with respect to a set of observables and the incompatibility of those observables, namely the impossibility of joint measurement of those observables. Now, incompatibility breaking channel, that means if I apply my channel on the observables of a given set, and if the output observables will become compatible, such a channel is called incompatibility breaking. So if my observable set is just a set of 2 observables, then it's 2 IBC. If it is 3 observables, it's 3 IBC, so on and so forth. Now, these people in this paper by Franco Nori and his collaborator, they have shown that the incompatibility breaking channel and steerability breaking channel, they are basically equivalent, which is expected from the result that I mentioned. So basically, to characterize incompatibility breaking channel, it is enough to characterize steerability breaking channels. Okay. So now let me um, go to this. I'll stop sharing. I'll look. I'll share another file. Let me see. Uh, let's do it. Yes, 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 yes. Is it visible? My
Yeah, not yet.
okay.
Yeah,
What about now?
it's coming now. Yeah. Yes. It is visible now.
It's visible, right?
Yeah, yeah.
Okay, okay. So now I'll talk about these the relation between incompatibility breaking and non-locality breaking. Okay, so this part I'll just leave because this I have described already. Okay, so what is incompatibility breaking channel? Although I mentioned already, but let me will mention it here. So any quantum channel E from the set of all bounded linear operators on the Hilbert space H A to the set of all bounded linear operator H B is said to be incompatibility breaking if the action of this channel on um, observables of a set capital A. So E of A means basically this is the collection of set of observables where E is acting on each such observable from the set capital A. If the set is incompatible, that means the observables in that output set are compatible, so you can jointly measure them. Okay, so if a channel E, quantum channel, breaks incompatibility of every class of n observable, that means I take a class A where there are n observables, and if it breaks incompatibility of every such class of n observables, then it is said to be NIBC. So n is equal to 2 means 2 IBC, n is equal to 3 means 3 IBC, so on and so forth. And as you can verify that, 2 IBC is the largest set in this picture. Uh, 3 IBC is a smaller subset. 4 IBC is even a smaller subset, so on and so forth. And IBC is the set of all channels. So IBC is a channel, or this set of IBC. So this IBC corresponds to set of all such channel, where each such channel breaks incompatibility of any set of observers. And as you can argue that entanglement breaking channel, set of all entanglement breaking channel for the given system is a subset of this. All these are convex sets. So EBC is contained in every system. Okay, and this is the this paper of Hinoseri and collaborators in 2015. So this is the notion of IBC, incompatibility breaking channel. And as I said, incompatibility breaking channel is equivalent to steerability breaking channel. Okay, so what I'll show you here is that, well, is my mistake. So this, it should be just E, not E tensor identity, just E. Similarly, E star, it should be just E. So E star means E dagger. So if E is a 2 IBC, that means 2 incompatibility breaking channel, then its conjugate channel. So you see, if a quantum channel has Klaus operators A1, A2, A3, etc., then its conjugate channel E dagger has Klaus operators A1 dagger, A2 dagger, etc. Okay? And if you know E is a unital channel, that means identity goes to identity, then E dagger will be a trace preserving channel, the conjugate channel. So it says that if E is 2 IBC, then E dagger is conjugate channel is Bell CHSH non-locality breaking. So how to prove that? So I'll just go through it briefly. So let's assume that this E is 2 IBC. So then by this application of this channel on Alice's side, so I have a bipartite state, rho AB. So application of this channel on Alice's side, okay. So this is basically 2 qubit state. So Alice has one of the two observables A1 and A2, two outcome observables, and Bob has one of the two observables B1 and B2. So I take these trace of rho and the Bell CHSH operator after the action of the channel on A1 and A2, Alice's side. Okay. So if this is, let's assume that this is 2 IBC. So, this in the Bell CHS, in Bell inequality, not just Bell CHS, any Bell type inequality, in order to have violation of the inequality, you need to have observables on each side to be incompatible. If you consider compatible observables, it will not give rise to violation of any such Bell inequality. And in particular for Bell CHS inequality, both the observables per side should be incompatible. Otherwise, you will not get violation. So because this E is 2 IBC, so therefore when E acts on uh, observables, two observables of a given set, the two observables become compatible, and therefore it will not give rise to get Bell violation. Therefore, this inequality will be satisfied. Whatever be your choice of your 2 qubit state row, observables A1, A2 for Alice, observables B1, B2 for Bob. Okay, now you split this. Okay, so if you split this, it will be of this form. And then, because in trace you can basically uh, reverse the role of action of the channel on observable to action of the conjugate channel on rho. So when we say conjugate channel, this E dagger or E star here is acting on one side of this bipartite state, these 2 qubit state, not on both. So this is acting on one side. So now if I can change this, replace this by the action of the conjugate channel on rho, and you see that this is less than equal to 2. And what does it mean? It means that this means that, so, and this rho can be any 2 qubit state. So therefore this E star on rho, one side of rho, will be any 2 qubit state as a result. And this tells you, therefore, that this channel E star is a non-locality breaking channel. Now, you might be, so one should be cautious here, because I call this E star as a channel, although I haven't mentioned whether it is trace preserving or not. But for non-locality, it doesn't matter, because what you can do is you can apply this E star on rho and then divide it by the trace of this E star of rho. So that is also fine. Anyway, so basically, you see that this, if E is 2 IBC, then its conjugate channel is CHSH non-locality breaking. Now I assume that E is a unital channel and it is also CHSH non-locality breaking. And therefore, because E is unital, its conjugate channel is trace preserving. Then you can show that this E star, the conjugate channel, is 2 IBC. Okay, proof goes in the same way, that you take the this uh, you take this the average value of this Bell operator, A1, A2, B1, B2. A1, A2 are the two observables on Alice's side, B1, B2 observables on Bob's side, and curly B is the Bell operator. And you apply the channel on this 2 qubit state row, and because it is CHS non-locality breaking, this inequality should be satisfied, whatever be your choice of row, A1, A2, B1, B2. And then again, you can reverse back, so you can take the action of E dagger or E star on the observable A1, and this inequality will tell you that basically these mm, this E star is 2 IBC, because E star is again a channel, it's a trace preserving, and because this is satisfied, whatever be your choice of E1, A1, A2, B1, B2, and rho, if this is satisfied, therefore these E star of A1 and E star of A2 should be compatible. As I said, in order to have violation of Bell inequality, it is, you will have to consider incompatible observables. And this basically because of the arbitrariness of A1, A2, B1, B2, A1, A2 basically, these are compatible, and therefore this is a E star is a 2 IBC. Okay, so you see that there is a basically one-to-one correspondence between CHSH non-locality breaking qubit channel and 2 IBC qubit channels. Now, in principle, this can be extended to any Bell type inequality, and not just 2 IBC. It can be extended to NIBC, etc. So, in principle, this can be extended. So, such a connection should exist for all other inequalities also, and not just for 2 IBC, NIBC also. Okay. So, having said that, now the question is that can I get to see such a connection if I go beyond this bipartite Bell type inequality, namely the CHSH inequality? What happens to this connection of non-locality breaking and incompatibility breaking if I consider, let's say, a tripartite Bell type inequality? Okay. Now, as I said earlier, that for tripartite or multipartite Bell type inequality, we don't have the necessary sufficient condition for a state to satisfy or violate that inequality. Okay, depending upon the state parameters. Okay, now there is this well-known inequality called Svetlitzny's inequality for tripartite system, which looks at, so violation of such inequality will guarantee genuine non-locality of a tripartite system. Okay, so basically it is of this form. So you want to simulate these tripartite probability, joint probability, P, A, B, C given X, Y, Z, which has this bilocal form. So it can be like uh, outcome B, C given, it should not be XY, it should be YZ, sorry. So we see outcome YZ times this A given X with this hidden variable lambda, whose probability is Q lambda, or it can be of this bilocal form AC given X and Z, or it can be of this form AB given XY, where these are the probabilities. So Q lambda plus Q mu plus Q nu should be equal to 1. So if a state I mean the measurement statistics of a state has this kind of structure, then it will have a, basically the bilocal hidden variable model, and violation. And if a state do not have such thing, then violation of the corresponding inequality involving such probabilities will tell us that the state does not have such a bilocal hidden variable model. Okay, so this weightlessness inequality is basically, in the simplest form, is of this form, where Alice has one of the two outcome observables A and A prime. These two outcomes can be +1 and -1. Bob has one of the two outcomes observables B and B prime, each of which is ±1 value. And similarly, Charlie has one of the two outcome observables C and C prime, each of which ±1 value. So the observable, Bell type observable, which he calls Wetlichny operator S, is basically of this form. So you can see that each inside this bracket is a Bell type of observable. Okay, where this each observable is basically, it's a spin observable, a spin half observable. Okay, so it is known that um, any state having this bilocal description, as I mentioned earlier, the average value of this Wetlichny's operator with respect to that state is less than equal to 1. So the so-called classical value, maximum classical value is 4, and any value greater than 4 will be violation. In fact, it can be shown that if I take a 3-qubit state rho and calculate this operator value S, it is the maximum value of these maximum average value of S with respect to rho is less than or equal to 4 times lambda 1, and this is a tight bound, while lambda 1 is the maximum singular value of this bipartite matrix, which is in this case 3 by, basically it is a 3 by 9 matrix. So mj comma ik, because ijk's are like this. So mij is basically trace of rho I tensor rho j tensor rho k. So you get to see some bound on a bound. This is a kind of tighter bound on the maximum average value of this Wetlichny's operator by any 3-qubit state. Okay. Unfortunately, we don't have any any necessary sufficient condition, as I said, that given a 3-qubit state rho, whether it will violate, whether the average value of S will be greater than equal to 4, that greater than 4, that is the classical value, that we don't know. Okay. So in particular, if for a given state rho, this lambda 1 turns out to be less than equal to 1, then of course it will satisfy whatever be the choice of your observables. Okay, and in that case, so our goal will be satisfied, right? Okay, so in the absence of such a necessary sufficient condition, what we have done, at least to get some insight where to look at or what kind of properties one should look at, so we considered different kinds of examples. So let's consider this generalized GHG state alpha 000 plus beta 111, where alpha beta are real, alpha square plus beta square is equal to 1, and you can write it the projection on this high in terms of this Pauli basis. Simple, right? And then you can look at this matrix 3 by 9 matrix. So this 3 by 9 matrix, you remember, this is the 3 by 9 matrix mj comma ik, where mij is of this form. So corresponding to this generalized GHG state, you can write down this 3 by 9 matrix, which I call M1, and look at its largest singular values. In fact, it has two equal singular values, these 2 alpha beta square root times square root of 2, and this another one is alpha square minus beta square. And this maximum Wetlichny's operator, assuming I mean, if you calculate this West-Lattice operator corresponding to the state, and if you maximize over all observables, you will get to see this value 8 root 2 alpha beta. So basically, if you uh, I'm not saying that this is the maximum, but if you look at this 4 times lambda 1, so this is the maximum that you will get. So maximum value of this, and the violation of this wet distance inequality, that means this should be greater than 4. This will correspond to alpha beta greater than 1 upon 2. Okay, and the and for this generalized GHG state, we know that maximum violation of the GHG of this wet distance inequality is obtained when alpha is equal to beta is equal to 1 upon 2, namely the GHG state. Okay, so I'll just keep this part because this is not the main idea. So basically, I told you that there is this notion of strong non-locality and hidden non-locality, etc. So I mean, one can extend it for more than two parties also. So it's fine. Um, so now what we have done is the channel, the qubit channel that we considered, which acts on one of these three qubit, is the channel which is basically, you know identity goes to identity, and sigma x goes to eta times sigma x, sigma y goes to eta times sigma y, sigma z goes to eta times sigma z, where eta is some real number between 0 and 1. Okay, so such a channel is of course unital channel, and if I take that channel and then I apply it on this one side of this generalized GHG state, or of this state 3 qubit state MS, which is of this form, is also entangled in general, and a state which is a mixture of GHG state and the this I2 tensor product I bar. I bar is of course not identity, but something diagonal one. So anyway, so if I look at the action of such a channel, if you look at this tabular form, you see that this wet distance violation for the generalized GHG state correspond to alpha beta greater than 1 upon 2 root 2. For mixed slice states, sorry, for maximum slice state, this one MS, this corresponds to alpha square plus 2 beta square greater than 1. And modified GHG state, this is the modified GHG state, which is p greater than 1 upon root 2. And for non-locality breaking condition, the parameter eta that I mentioned for the unital channel, it has to satisfy this thing. Eta must be less than equal to 1 upon 2 root 2 times alpha beta. Eta must be less than equal to this one, and eta must be less than equal to 1 upon 3 root 2. And incompatibility breaking condition, namely the observables will become incompatible. Now, for qubit observables, you know, if I look at when I add noise, that means I white noise to it, it is known that the value of eta, that means the action of this channel, so value of eta should be less than equal to 1 upon root 2. So under the action of the channel, what happens, the qubit observables will become noisy observables. It will have unsharpness and biasness also. So in each case, eta is less than equal to 1 upon root 2 for incompatibility breaking. So you see that there is a mismatch here between the incompatibility breaking and non-locality breaking. So here is the plot. So this left-hand side plot is for generalized GHG state. So this color, this one, the pink one, so every point inside it corresponds to non-locality breaking. So this is a plot, eta versus alpha. Alpha is the coefficient, alpha 0, 0, 0 plus beta 1, 1, 1. So you see that this line, this dotted horizontal line corresponds to eta is equal to 1 upon root 2. And this is the range, entire range for non-locality breaking. Okay, so this is for the generalized GHG state. So you see that only at this point, which corresponds to, I think, the minimum value of basically this. So eta is equal to 1 upon root 2. So in this case only, you see that there is a match between the non-locality breaking and incompatibility breaking. Uh, Here, this is for this kind of states, this MS, this is the maximally sliced states. So for this state, you see that initially at this level, there is a match between the incompatibility breaking and non-locality breaking. And here, this is for the mixture of GHG state and this noise. So here you see that there is a match at this level. So you see that when you go to tripartite scenario, 3 qubit scenario, this equivalence or the one-to-one relation between incompatibility breaking and non-locality breaking does not hold good. Okay. So one can ask what happens if I apply the channel on 2 of the qubits or 3 of the qubits. I mean, even situation will become worse in that case, actually. So with this, I'll conclude. So basically, we show an equivalence relation. I mean, kind of one-to-one correspondence between CHSH non-locality breaking and incompatibility breaking. Of course, this is two incompatibility, but as I said, this can be generalized for other inequalities, for NIBCs, etc. The tripartite scenario, what we have done, the examples, it shows that there is a gap between this non-locality breaking and incompatibility breaking. But of course, we don't have the full picture because we don't have the necessary sufficient condition to test the split-within inequality violation. Okay? And what we have seen is that for certain range of you know parameters, certain range of channel and state parameters, incompatibility assures non-locality or generalized GHG state and maximally such states. Okay. Thank you for your patience.
Yeah, thank you, Professor Ghosh, for
Yeah.
your intense talk. And now it is open for questions. Participants can write their questions in the chat box, as well as they can unmute themselves and ask directly.
Where can I see the chat box?
Yeah, so there is in chat box, there is no.
Uh-huh.
Yeah, so meanwhile, just, uh, 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 I'll point out to one thing that, is there any uh, direct relation of non-classicality and the uh, quantifying entanglement for many body systems? Like, it's a very general aspect. Do you want to elaborate, or there's something about it?
Uh, so
So,
can
the
you
measurement of non-classicality and also the entanglement. So, yeah.
okay? So of course, this is something different from what I mentioned here.
Yeah, yeah, of course, yeah.
Um, so you know that for um, okay, so there is a connection between non-classicality in the sense of coherence. Okay. Like if I take a system and a state of a quantum system and then express it in terms of some basis, and if it has some coherence in that basis, namely off diagonal terms, then we say that it has a kind of non-classicality. Now operationally, what does it mean? It has a different perspective. Okay, so coherence can generate something. It's basically kind of superposition. Now such a coherence can be in principle transformed into entanglement. Okay, so you know that for the case of infinite continuous variable system, we can transfer non-classical to optical non-classicality into entanglement through the beam splitter action, right? So similar thing of course can be done, and people have done it in the case of finite dimensional systems also. Um, so, in principle, one can get a connection between the amount of coherence and the amount of entanglement that it can produce. Now, operationally, these can be different in the sense that
Yes.
That coherence, I mean, how will you use it to achieve something, and this entanglement, how will you use it to achieve something? That may be different, but yes, there is a relation between these two, both in the infinite dimensional case, I mean, the in the quantum optical scenario, as well as in the finite dimensional cases.
Yeah. Okay, thank you. So if there's no other questions, then let us thank the speaker once again for delivering the talk here. So,
Thank
thank
you.
you, Mr. Ghosh.